Now the measurement of conductivity of the ionic solutions, I have told you that it is basically done with the help of conductivity cells, because those conductivity cells are used to compare the conductivity of the different electrolytes, and out of this we can easily make out which is a better electrolyte. But remember, the kappa varies with the charge of the size of the ions, the charge on the ions, and the concentration. So alone kappa will not give us the complete information, and that is why the most important thing to incorporate is the concentration. So that is why another term called molar conductance, whose symbol is lambda and MOL is written in the subscript, is used to explain the electrolytic conductance in a much meaningful way. So what is in the molar conductances? It is the conductance shown by all the ions given out by 1 mole of the electrolyte taken in V cubic centimeter volume of the electrolyte in a cell in which the distance between the electrodes is 1 centimeter and the surface area of the electrodes is such that whole of the solution lies in between. What does it mean? It means that we can find out lambda as kappa into volume, because kappa we know is the conductance shown by the 1 ml of the electrolyte, and if we are having 500 ml of the electrolyte, we will simply multiply it by volume. But this term is actually having the concentration in a hidden way. So we can write it like this as kappa into 1000 upon molarity, because we know that molarity is equal to number of moles into 1000 upon V, and if we have number of moles of the solute as 1, the volume will be 1000 upon molarity. Now from this term we can easily make out that this molar conductance is inversely proportional to the concentration, which is expressed in terms of molarity. Now the higher is the molarity of the electrolyte, lesser will be the molar conductance, and or vice versa. So from this term we can easily make out that how it is the concentration which affects it, and this term completes the basic of the electrolytic conductance. We can write down this formula in another way, and the another way is that this lambda molar can be written as, because kappa is 1 by R into L into A into 1000 by M. So this is what is the complete formula is, where 1 by R is the conductance. The moment it is multiplied by L by A, which is cell constant, it becomes conductivity, and the moment it is multiplied by 1000 by M, it becomes molar conductance. What is the unit now of this molar conductances? The unit of this molar conductance will be, it will be ohms inverse centimeter inverse into 1 upon moles into cubic centimeter. Now we can write it like this: ohms inverse centimeter square per mole. So this is what is the unit of the molar conductances, and this is how it is being used. And let us see now in a numerical that how it can be used to find out the molar conductance of the electrolytes. Let us see a numerical how we can find out the molar conductance of the electrolytes. It says find the molar conductance of 0.1 molar NaCl solution, which shows a resistance of 20 ohms in a cell of cell constant 2 per centimeter. So what is given to us is the cell constant as 2 per centimeter, resistance as 20 ohms, and the concentration or molarity is 0.1 molar. This is already given to us. We know the formula that the molar conductance can be determined as 1 by R into L by A into 1000 upon M. So it's 1 by 20 into 2 into 1000 upon 0.1. So it will be 10. This gets cancelled out from this, so it comes out to be 1000 centimeter square ohms inverse mole inverse. So this is what is the answer is. So it's a very simple formula, and mostly the direct values are given, This can be placed like this to find out the molar conductance of the any given electrolyte.